Why force is not equal to mass times velocity. Why the acceleration in F equals ma will not lead to infinite velocity. Why force cannot be equal to mass times acceleration to the power of 1.0001. Is force a redundant concept? Welcome to Zero Physics. In this video, we are going to explore the equation F equals ma. Force is equal to mass times acceleration, or F equals ma. This simple equation is one of the most famous equations in physics. However, there are several issues or problems with this equation. The first problem is why force is not equal to mass times velocity. Intuitively, we might think that an object moving at a constant velocity of 10 meters per second would generate more force than an object moving at 5 meters per second. However, when we apply the equation F equals ma to this situation, we find that the force generated by both objects is actually zero. So why can't force be equal to mass times velocity? The second problem is why F equals ma does not lead to infinite velocity. According to F equals ma, if we apply a continuous force of 10 newtons to an object with a mass of 5 kilograms, the object will accelerate at a rate of 2 meters per second squared. This means that the object's velocity will increase by 2 meters per second every second. If this continued, the object's velocity would eventually exceed the speed of light after 4.75 years, requiring an enormous amount of energy. However, generating this amount of energy is not that difficult for humans. The equation F equals ma seems to contradict the principles of special relativity. The third problem is why force cannot be equal to mass times acceleration to the power of 1.0001. We know that force is exactly equal to mass times acceleration. However, our nature does not require force to be precisely equal to this product. So, what would happen if force were equal to mass times acceleration to the power of 1.0001? The fourth problem is whether force is a redundant concept. In fact, we can describe the motion of an object without using the concept of force. For example, during a collision between objects, we can simply apply the principle of conservation of momentum to describe the motion, without explicitly considering the force. So now, we are going to answer all these questions. To understand why force is not equal to mass times velocity, we need to consider three fundamental facts. The first fact that you need to accept is stationary and uniform velocity are actually equivalent. For instance, you may feel stationary while lying on your bed watching this video. However, the Earth is constantly rotating and orbiting the Sun, so you are actually moving with the Earth. This concept is related to the inertial frame of reference, but we won't delve into the details here. For now, it's important to accept that we cannot distinguish between being stationary and having a uniform velocity. The second fact we need to accept is that force is only generated when there is a change in velocity. This is based on Newton's second law, which states that force is the rate of change of momentum. Therefore, force will be generated only when an object's velocity changes. The third fact to accept is that every physical process in the universe takes a certain amount of time and is not instantaneous. There is always an interaction time involved in any physical process, and the minimum time for an interaction to occur is known as the Planck time. Now, let's address our first question: why is force not equal to mass times velocity? Firstly, if force were equal to mass times velocity, force would appear different to different observers. This would contradict the principle of relativity, which states that the laws of physics should be the same for all observers in inertial frames of reference. Secondly, the equation F equals mv would be meaningless because force is only generated when there is a change in velocity. An object moving at a constant velocity of 10 meters per second would not generate any force unless it comes to a stop or experiences a change in velocity. Thirdly, collisions are not instantaneous processes. There is a very short time interval, known as the time of impact, for an object changes its velocity from 10 meters per second to 0. This time interval depends on the material involved. Therefore, force cannot be equal to mass times velocity because the change in velocity is important to generate force. By considering these facts, we can conclude that force cannot be equal to mass times velocity. According to the famous equation E equals mc squared, when the kinetic energy of an object increases, its mass also increases. This implies that mass is not a constant but rather a variable that depends on velocity. As velocity increases, mass of the object increases as well. Consequently, a greater force is required to accelerate the object with increasing mass. Therefore, an infinite amount of force or energy is needed to accelerate an object to the speed of light, which is practically impossible to achieve. This helps explain why we cannot exceed the speed of light. It is worth noting that there is ongoing debate regarding the concept of relativistic mass, whether mass increases with velocity. A better explanation for why we can't exceed speed of light is due to the causality and geometry of space-time. However, both explanations are mathematically equivalent. Therefore, using the concept of relativistic mass to explain the equation F equals ma should not be any problem. In conclusion, by considering E equals mc squared, we know that the equation F equals ma would not lead to infinite velocity. While numerous experiments have confirmed the validity of the equation F equals ma, however, it is important to recognize that there may be unavoidable uncertainties in any experimental measurements. Actually, it is possible for the power of acceleration equals to 1.0001, which makes force is not exactly equal to mass times acceleration. However, it would lead to various problematic consequences. Firstly, in dimensional analysis, we would encounter difficulties in understanding the meaning of a quantity raised to the power of 1.0001. The unit of measurement becomes unclear and potentially inconsistent. Secondly, the additive nature of forces would be violated, as the equation becomes nonlinear. This would introduce complexities in calculating and combining forces, undermining the intuitive understanding of force as an additive quantity. Thirdly, the equality between inertial mass and gravitational mass, a fundamental principle in physics, may no longer hold true. It is worth noting that this question bears similarities to the inquiry of why Coulomb's force and gravitational force obey the inverse square law. Why the power can't be 2.0001 or any other value. This is ultimately due to the fact that we live in a three-dimensional world, and the inverse square law arises from the geometry of space. We will discuss this in our future video. In conclusion, force must be exactly equal to mass-time acceleration. In our universe, there are four fundamental components: space, time, matter, and interaction. Space and time combine to form a four-dimensional spacetime, while matter refers to all the objects existing within this spacetime. The behavior of matter is governed by the four fundamental interactions. When we consider the equation F equals ma, it encompasses these important physical quantities. Describing space, time, and matter is relatively straightforward. We just need to use the base quantities, mass, length, and time to describe it. However, when it comes to describe the interaction or force, we need to express it in terms of mass, length, and time. For instance, if we have a force of 5 newtons, it means that when this force is applied, a 5 kilogram object will accelerate at a rate of 1 meter per second squared. A 1 kilogram object would accelerate at 5 meters per second squared. And a 2 kilogram object would accelerate at 2.5 meters per second squared, and so on. This is the meaning of 5 newtons of force. In this sense, if we define force using the equation F equals ma, the definition itself is not fundamental. It may seem that the concept of force is not truly necessary because the equation F equals ma can be used solely to express the relationship between mass and acceleration given a specific strength of interaction. When the strength of the interaction remains the same, mass and acceleration are merely a ratio. The concept of force was invented by humans to simplify calculations and describe motion more conveniently. Moreover, even in collisions where force is generated, we can describe the motion by applying the principle of conservation of momentum without explicitly using the concept of force. In advanced physics, particularly in quantum field theory, physicists often prefer to use energy or the Lagrangian to describe motion. There are several reasons for this. Firstly, energy is a scalar quantity, which is more convenient than force, which is a vector quantity. Secondly, Energy is considered more fundamental because it can exist independently of force. However, we will discuss these in our future video. For now, it is important to acknowledge that force can be seen as a redundant concept that is not as fundamental as other physical quantities. Thank you for joining us in this exploration of the equation F equals ma. If you found this video informative and thought-provoking, we invite you to subscribe to our channel for more engaging content like this. That's all from this video. Thanks for watching.